Last time we looked at graphing functions, and in particular, we looked at the graphs of 6 common functions that we want to be able to remember and recognize the graphs of. They included the functions f of x equals x, f of x equals x squared, f of x equals x cubed, f of x equals the absolute value of x, f of x equals the square root of x, and f of x equals the cube root of x. And we looked at these 6 functions and we looked at their graphs, and we can spend some time to memorize these, or at least to remember their general shape. But of course, most functions don't look like this. Most functions are more complicated. I might have a function that looks like f of x equals -3 times 1/2 x plus 1 squared plus 4. Something like this. Well, it turns out that we can figure out what the graph of this function looks like without having to go through the process of plotting out a bunch of points. We can recognize this function, this complicated function, as a transformation of one of our basic 6 functions. In this case, it's going to be a transformation of the function x squared, and we can recognize that by seeing that there's an x in the problem that's being raised to the power 2. Now, of course, there are a lot of other things that are happening here. We've got numbers that are being multiplied both outside these parentheses and inside them. We've got numbers that are being added both inside the parentheses and outside of them. We could have numbers being subtracted or divided as well, just as easily. And our goal for today is to understand how all of these different changes that you can make to these functions affect their graph. What does multiplying this -3 factor in the function do to the graph? And what does adding 4 do, and adding 1 and multiplying by 1/2, and so forth and so on. And so that's going to be our goal for today. We're going to be looking at 3 different kinds of transformations. And the 3 transformations are translations, and these are shifts horizontally or vertically. These types of transformations will take the graph, keep its same shape, but move it to a different place on the plane. We will have reflections, which will reflect the graph across either the x-axis or the y-axis. And then we have scaling, which involves stretching or compressing. And that will, these stretches and compresses will happen either vertically or horizontally. So we're going to look at these 3 transformations in sequence, and we're going to look at what the different kinds of ways that we change the function do to the graph of the function. There are a couple of general principles that I want to mention that apply to all of these transformations, though, before we get started into the details. So, as a general rule, numbers added, subtracted, multiplied, or divided against the variable before the function applies affect the graph horizontally. And numbers applied outside the function, the basic function, I should say, affect the graph vertically. Now, let's look at this example that I had before, and I'll illustrate what I mean. If we want to recognize this function as being a translation, or a transformation, I should say, of the basic function x squared, well, then we can see that we can identify 4 things that have happened to it. Now, in fact, one of those things we're going to break up into 2 separate ones, so we're actually going to see this as 5 different things happening, but we'll get to that in a second. What we have from the basic x squared function that we understand, we can see that we've multiplied a 1/2 by the x, and we've added a 1, and both of these transformations that we've done, both of these changes that we've made to the function formula have happened inside the parentheses. They've happened to the variable x before anything else has, before the function has applied. The basic function we're working with in this case is the squaring function that takes the number x and turns it into x squared. Well, the 1/2 and the 1 that are being applied to this x, 1 multiplied and 1 added, are both happening before the squaring happens. In terms of order of operations, all those things are inside the parenthesis. All those things happen to the x first, and then the result of that computation gets squared in the formula. So what that means, based on the general rule up above, is that the 1/2 and the 1 are going to affect the graph horizontally. They're going to accomplish horizontal changes in the graph. On the other hand, the -3 and the +4 are both applying outside of the function. We have our expression 1/2 x plus 1, we square it, and then after we square it in this expression, then we multiply by a -3, and then we add a 4, and those 2 numbers are going to affect the graph vertically. They're going to accomplish changes in the graph in the vertical direction. So moving up or moving down, stretching or squashing in the vertical direction, etc. We will make all of these concepts very precise in just a moment. The other idea that I want us to keep in mind that we're going to use in order to understand what's happening with all of these transformations is that the transformations that we talk about can be applied to the individual points on the graph. So when we're going to start talking about moving the graph around or rotating it, or reflecting it rather, or scaling it, stretching it, squashing it, those are going to be things that we can all apply just to the points on the graph. And so one of our common strategies is going to be just taking a few points in the general graph, applying the transformations to get a new set of points, and then plotting the graph through our new set. And as I said, we will see this here. All right, we have three different kinds of transformations we're going to talk about: translations, reflections, and scalings. And translation is the first kind that we're going to talk about. So let's look at translations. And the types of changes that give us translations are when we add or subtract a number. So let's compare the functions f of x equals x squared. So this is our basic function. We're going to look at this function a lot and see how it gets transformed. And we want to compare the function g of x, which is x squared plus 3. So let's go ahead and just sketch these functions out and see what we get. So I'm going to make a table over here where I'm going to take our values of x, some values of x, and then I'll get the values of f of x and the values of g of x, and we'll use these to graph the functions. So the points that I'll use are 0, 1, -1, 2, and -2. And we see that if x is 0, f of x is 0 squared, which is 0. 1 squared is 1. -1 squared is 1. 2 squared is 4. -2 squared is 4. And so this gives us a bunch of points on the function f. So let's go ahead and sketch those out. We've got, let me do f in red. So we have the point 0, 0, then the point 1, 1, point -1, 1, the point 2, 4, and the point -2, 4. And we've seen this shape a bunch of times by now. This is our parabola shape. That goes up from here. This is in fact our basic x squared function. Now let's look at what happens when we get g of x, which is x squared plus 3. So we'll do a few of these until we start to see the pattern. So we have that g of 0 is equal to 0 squared plus 3, which is 3. G of 1 is 1 squared plus 3. Now 1 squared is 1. We actually already knew that because that's just the thing that we get out of f, which gives us 4. G of -1 is -1 squared plus 3, which is 4. G of 2 is 2 squared plus 3. 2 squared is 4. Adding 3 gives us 7. G of -2 gives us -2 squared plus 3, which is again 7. So we get the points 3, 4, 4, 7, and 7. And notice what has happened here. Because the function g of x, which I will sketch in blue, has a formula where part of the formula, the x squared, is exactly the same as the formula for x. The only thing that changes between the graphs of f and g is that the y values of the points that we find are 3 higher. So on g, we're going to have the point 0, 3, 1, 4, and 2, 7, -1, 4, and -2, 7. And so what we'll get is that our function g is also a parabola, but one that sits higher on the graph. And in fact, we can say more. It doesn't just sit higher, we can say exactly what sort of transformation has happened. The entire graph has shifted up exactly 3 units. Look at what's happened here. If we take every point on our original function and move it straight up by 3 units, we get a point on the graph of g. So, uh, what this example shows is the general principle that adding a number to a function on the outside of everything will shift the function vertically. Now in this case, because we've added a 3, that has increased the y values of all of the points on the graph by 3, which in other words has shifted the whole graph up by 3. If we had subtracted a number, we would have dropped the graph and the graph would have shifted downwards. So this gives us the general principle for what happens when you add a number on the outside of the function. Let's look at another function though. Let's use this same graph and see the other kind of transformation that we can have, or translation. The other kind of translation we can have is a horizontal one. Now the general rule that I mentioned before says that vertical changes to the graph occur when you add or when you change a number outside of the function. When you've got the variable, it's had its function applied to it, in this case x squared, the basic function, and then something else happens to it. Whereas horizontal changes occur when you make a change to the x values before applying the basic function. So let's look at h of x, which is x plus, now I'm going to, in order to save us some space here, I'm going to take a particular point here. Let's let h of x be x plus 7 squared. Now I'm not going to use these same points that we did over here. I'm going to use another set of points in order to make the graph clear. We have that h of negative 7 is equal to negative 7 plus 7 squared, which is 0. So that tells us that h will be in green now. 2, 3, 4, 5, 6, 7. This tells us that h of negative 7 is 0, which means that the point negative 7, comma 0 appears on the graph of h. Furthermore, we have h of negative 6 is equal to negative 6 plus 7 squared. Now negative 6 plus 7 is 1, and 1 squared is 1. H of negative 8 is equal to negative 8 plus 7 squared, which is negative 1 squared, which is again 1. H of negative, we want negative 5. So negative 5 plus 7 squared, which is 4. And h of negative 9 is negative 9 plus 7 squared, which is, again, 4. And the reason why I've chosen these particular numbers is that we see the same sort of pattern emerging, the same shape of the graph emerging. So we have the point negative 6, comma 1. We have the point negative 8, comma 1. And then we have the points negative 5, comma 4, and negative 9, comma 4. And so what we see is that the graph of h is, in fact, a shifted version of the original graph of the function f. Only in this case, it's been shifted to the left. And every point has been shifted to the left by 7 units. The point 0, 0 has made its way over to the point negative 7, 0. The point negative 1, 1 gets mapped over here onto the point negative 8, 1. And similarly for the other points. We can see that by changing the function to x plus 7 squared instead of x squared, we have shifted the graph left by 7 units. So let's summarize what we've seen here, because the pattern that we've seen here in fact applies to all functions. So let's write it this way. So translations. The graph of, let me write it as y equals f of x plus k is the graph of y equals f of x shifted vertically by the absolute value of k units, and that shift is upward if k is positive, and downward if k is negative. And then, similarly, the graph of y equals f of x plus k is the graph of y equals f of x, but shifted or translated horizontally by the absolute value of k units. And this is leftward if k is positive, as we saw in the previous example, and rightward if k is negative. So, a couple things to point out here. The first one is that when we are accomplishing our horizontal transformations, as in the second point here, things typically work in the opposite way of sort of our intuitive way of doing things. And the reasons for this are not complicated, but you're better off generally just remembering that things sort of work backwards when you're looking at the horizontal transformations. So normally we associate positive numbers with the right-hand side of the graph, and that's because that's where the positive x values are. But in fact, if we're adding a number on the inside of the function with the variable, that's actually going to accomplish a leftward shift in the function, and subtracting a number will accomplish a rightward shift. Let's do some examples. So first of all, I want to show an example where we just start with the graph of a function. We're not going to say what this function is or anything. We're just going to give it a few points, and we're going to see how the translation occurs. So let's say that it goes from the point -7, 7, 1 to the point -3, 5 to the point 2, 5 to the point 4, 1, and that's it. We've got this graph here made up of a few line segments. Now notice this is the graph of a function. It passes the vertical line test. So let's suppose that we want to graph the functions y equals f of x minus 3, y equals f of x plus 2, and y equals f of x minus 1 plus 1. So these are three separate questions, and for each one of them, we want to start by translating the points and then connecting up the new points that we've created. So for part 1, let's look at y equals f of x minus 3. So here we notice that the change that's been made is on the outside of the function f. What that means is that we have a vertical change. Now, the vertical changes that we deal with work basically intuitively. Positive values mean shifting upwards, negative values mean shifting downwards. So this means that this function, the graph of this function is shifted downward by 3 units. Or in other words, we're going to subtract 3 from each y value on the graph. So we'll call this blue. One way that we can do this is we can take every point on the graph and subtract 3 from its y value. And what that will do is that'll give us a new point on the graph of the function y equals f of x minus 3. So we get negative 7 comma 2, negative 3 comma 2, 2 comma 2, and 4 comma negative 2. And there's our graph of the function y equals f of x minus 3. Now we can do the same thing with each of the other ones. If we want to get the graph of y equals f of x plus 2, we look at it and we say that, okay, well, this plus 2 is happening inside the function f, which means that this is a horizontal change to the graph. And because it's being added, it's a shift, it's a translation. So we're going to shift this function left by 2 units. Or in other words, we're going to subtract 2 from each y value. I'm sorry, not from each y value, from each x value. Sorry, that was a very important distinction to make there. So intuitively, things that are affecting the function close to the x are affecting the x values of the points of the function, and things that are on the outside of the function are affecting the y values of the function. So if we do that, then we can take each of these points and subtract 2 from their x values. So the point negative 7 comma 1 gets shifted over to the point negative 9 comma 1. The point negative 3 5 gets shifted over to negative 5 5. The point 2 5 gets shifted over to 0 5, and the point 4 1 gets shifted to the point 2 1. And so here we've just shifted everything to the left by 2. The shape of the graph is still the same. It's just been shifted to the left by doing this. Now, for the last one, let me go ahead and duplicate this on the next page. The function y equals f of x minus 1 plus 1, this is going to involve 2 separate transformations. So let me get this here. Let me get rid of the pieces that we had before. Sorry about that. Okay, so good enough. And so here's what we've got. And I just realized that I didn't line it up properly with the grid. There we go. All right, so now if we look at y equals f of x minus 1 plus 1, we can see that there are two changes that are being made. And in order to get from the graph that we have, the graph of f that we have, to the graph of the new function f of x minus 1 plus 1, which I'll do in green, we're going to do two separate translations. So we're going to start, we can start with either one really, but it's often a good idea to do your horizontal transformations first, think about those first, and then move on to your vertical ones. So here we've got a translation happening because we're adding or subtracting a number to x. Now, because we are subtracting 1 from x, this means that we're going to shift to the right by 1. Because it's with x, we kind of do the opposite of our intuition. Normally negative means move to the left, but in this case, negative means move to the right. With the 1 over here on the outside, this tells us that we're going to shift up by 1. Because we're adding 1 on the outside of the function. The things outside the function affect the graph vertically, so up or down, and they behave intuitively. So adding 1 means shifting up by 1. And so this graph will involve taking each of our points and moving them up 1 and to the right 1. So the point 41 becomes the point 52, the point 25 becomes the point 36, the point negative 35 becomes the point negative 26, and the point 71 becomes the negative 71 becomes the point negative 62. We've simply added 1 to the x values and the y values of each of our points here in order to get the translation of the graph. All right, let's do one more example with translations here, going back to our familiar function of x squared. So let's say we want to graph y equals, and we want x minus 1 squared minus 2. So what we can see is that this is a translation of the graph of x squared. So if I color code this, I can see that the function x squared is the base function. We want to see we want to break up this function into a base function and then transformations of it. All right, then we've got the transformation of subtracting 1 on the inside. And so this is going to be a horizontal shift of 1 to the right. And then the minus 2 on the outside gives us a vertical shift of 2 down. Down now because we are subtracting 2 on the outside. So a lot of times, the best way to go about graphing these things is to start off by graphing the familiar function, the function that we know, that we have memorized. So in this case, I'll make things slightly bigger than before. Now we know that the base function x squared contains the following points in its graph: 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. And let's go ahead and sketch that in. So that's what the graph of just y equals x squared looks like. And when you are doing this, if you're doing this by hand, I do strongly recommend labeling each of the graphs that you put down in order to make sure that you understand what's going on when you come back to review it, or even just as you're going through the problem. All right, so now we can see, we can look at the problem, look at the pieces that we've identified. We've identified two translations in this problem. One of them is a horizontal shift that's going to shift everything 1 to the right, and the other is a vertical shift that's going to shift everything 2 down. And we can do both of those at the same time. We can do all the translations that happen in the problem simultaneously. So every point we can find its translated version of it by moving 1 to the right and 2 down. So the point 0, 0 gets translated to the point 1, 2. The point 1, 1 gets translated to the point 2, negative 1. And notice all I'm doing here is I'm taking every point and I'm adding 1 to its x value, and I'm subtracting 2 from its y value, because each of these points are what we get when we shift to the right by 1 and down by 2. And so finishing up, we get negative 1, 2 as our last point. So now the green points are points on the graph of our of the function that we were working with, y equals x minus 1 squared minus 2. So let's fill in the graph of that. And there we go. So we can see that the graph of x minus 1 squared minus 2 looks just like the graph of y equals x squared, but it's been shifted. It's been shifted down and to the right. Minus 1 squared minus 2. So that's pretty much all there is to know about translations. If we can identify the horizontal shift and the vertical shift, it's simply a matter of taking every point on the original graph, shifting it horizontally and vertically as required by the problem, and then connecting the dots in the new positions of the points. So now let's go and talk about reflections. And again, let's look at one of our familiar functions. Let's look at y equals x squared. And reflections are going to involve multiplying by either by a negative 1. So let's compare y equals x squared, which again I'll do in red, and y equals negative x squared, which remember is just the same as negative 1 times x squared. So remember again the general principle that we have, that things that are applying after the base function, in this case the base function is again x squared, things that occur afterwards are going to affect the y values of the graph. It's going to affect the graph vertically, the y values of the points on the graph. And in particular, this means that we're going to multiply the y values on the graph by negative 1. So let's see what that's going to do. So if we start with our base function, we have 0, 0, 1, 1, and 2, 4 as before, negative 1, 1, and 2, negative 2, comma 4. And this is what our basic graph of y equals x squared looks like. Now, if we want the graph of y equals negative x squared, then that's going to multiply each one of the y values in the graph by a negative 1. So let's make a table here really quick. If we have x and we have negative x squared, and we take our points 0, 1, negative 1, 2, negative 2, then negative x squared in each of these cases is going to be, well, just the negative of the output of x squared. So if x is 1, negative x squared is negative 1. If x is negative 1, negative x squared is negative 1. When x is 2, negative x squared is negative 4. And when x is negative 2, negative x squared is negative 4. A momentary aside, remember that there's a difference between the expressions negative x squared and negative x squared. These two are not the same. The correct way to interpret a negative x squared without any parentheses is to put the parentheses around the x squared. You evaluate the squared first and then the negative ahead of it. And the reason for that is that exponents come before multiplication in order of operations, and a negative in front of an expression has the priority of multiplication in the order of operations process. So that means that the points on the graph of y equals negative x squared are the following. We've got 0, 0, 1, negative 1, negative 1, negative 1, 2, negative 4, and negative 2, negative 4. So we can see visually what's happened here quite easily. The graph has reflected across the x-axis. Now, even though we've said x-axis here, this is actually a vertical change. We've taken something that goes up and we've reflected it vertically to the other side of the x-axis. Every one of the points on the graph has reflected around the x-axis to the opposite point. And that's what happens when you multiply a negative number on the outside of a function like this. Writing a negative x squared will reflect the whole graph across the x-axis. And of course, we'll make this precise in a second. But first, we want to ask what happens when you multiply a negative 1 on the inside. Well, if you're guessing that it has a similar result, a similar reflection, but sort of going horizontally rather than vertically, well, you're exactly correct. And to see that, let's compare the functions y equals the square root of x with y equals the square root of negative x. And let's take some x and y values here. We want x, square root of x, and the square root of negative x. Now I'm going to try picking some x values that are easy to take the square root of. So if x is 0, the square root of x is 0. If x is 1, the square root of x is 1. If x is 4, the square root of x is 2. If x is 9, the square root of x is 3. Now, we do run into a little bit of an issue with the negative square root of x here. If x is 0, then the square root of negative x is the square root of negative 0, which is just the square root of 0, which is 0. That's fine. But then if x is 1, then we get the square root of negative 1, which is undefined. And similarly, the square root of negative 4 is undefined. The square root of negative 9 is undefined. Now, we have, of course, written these numbers as I, 2i, 3i earlier, but for the moment, for when graphing functions, we're only interested in real number outputs of these functions. However, so we see that 1, 4, and 9 don't work as inputs to the function square root of negative x. However, the numbers negative 1, negative 4, and negative 9 do. If x is negative 1, then the square root of negative x is the square root of negative negative 1, which is just the square root of 1, which is 1. And the square root of negative negative 4 is just the square root of 4, which is 2. And the square root of negative negative 9 is the square root of 9, which is 3. But then we similarly get undefined output for the original square root of x function. So let's graph this out and let's see what's going on here. All right. Now, for this problem, I'm going to go ahead and use a different scale for the horizontal and vertical axes, which is not something we want to do a lot, but is sometimes helpful. And the reason why I'm doing it here is because the x values that I have in my problem are much larger than the y values I have. So I'm going to let a single tick mark represent, or a single square on the grid represent 1 unit in the x direction, but only half a unit in the y direction here in order to help illustrate the graph. So if we want y equals the square root of x, then we're going to have a few points. We're going to have the point 0, 0, 1, 1, 4, 2, and 9, 3. And we've seen this before. This is the graph of y equals the square root of x. Well, now let's graph out y equals the square root of negative x, the thing that we get when we multiplied the x inside by a negative 1. And there we get the points 0, 0 again. But then we get the point negative 1, comma 1. And we get the point negative 4, comma 2. And we get the point negative 9, comma 3. And binding those together, we get this shape. So, as I said, we can see that we've got a similar reflection happening. We're just reflecting around the y-axis. Or, in other words, we are taking each of the points on our original graph, our red graph, and multiplying the x-coordinate of that point by a negative 1 in order to get the point on the new blue graph here. So let's summarize how reflections work. So reflections. The graph of y equals negative f of x is the graph of f reflected across the x-axis. Or in other words, each y value is multiplied by -1. The graph of y equals f of -x, if the negative happens inside the function, is the graph of x reflected across the y-axis. That is, with each x value multiplied by -1. So we can take examples, but rather than doing just an example with a single reflection, which is what we've seen before, let's see what happens when we combine a couple of things. Let's graph y equals -x plus, -x cubed plus 2. And we're going to do this a little bit loosely. So what we want to do is, again, we want to identify this as a transformation of a basic function. Now, again, the basic function that we want to use, I'm going to write in red here. And so here the basic function is the cubed function, which we know. We know that the x cubed function looks basically like this. There's y equals x cubed. It's got the point here at 0, 0, and that's the only point I'm going to keep track of for now. And then we see that there are two things happening to it. We see that there's a negative on the outside, which I'll go ahead and write out explicitly as -1. And there's a +2 on the outside also, which we see. And so we can identify the transformations that each of these things is doing. This -1 is happening on the outside of the function, which means that we're going to have a vertical reflection. That is a reflection across the x-axis. And then this +2 means that we're going to shift up by 2. Well, here's where we have to be careful, though, about order of operations. The order in which we applied the two translations when we had a combination of translations before didn't matter. If we shifted horizontally first and then vertically, we got the same result as if we shifted vertically and then horizontally. Nothing changed there. However, when you have reflections, and later when we have scalings and shifts happening together, the order does matter. Now, here's where, unfortunately, we have, again, a little bit of a difference between what happens with stuff outside, the stuff that's affecting the graph vertically, the y values, and the stuff that's happening inside the basic function. Now, in this problem, all the transformations are happening outside the basic function. You've got the x, you're cubing it, and then all the other stuff is happening. In this case, when you're dealing with the outside stuff, the vertical y value stuff, you apply the transformations in order of operations. So we apply the vertical transformations in order of operations. Meaning, we are going to reflect first, then shift. And that's because the reflection comes from a multiplication, the shift comes from an addition, and multiplication comes before addition in order of operations. Now, a lot of times when I work on a problem like this, I will actually sketch out some of the intermediate functions. So I've got my original function y equals x cubed. So first I will apply the reflection. And if I apply the reflection, I will get something that looks like this. Here, all I've done is I've taken my function, reflected it around the x-axis. And that'll give me y equals negative x cubed. Then I'll shift up by 2. And so that will move everything up, and instead of the point 0, 0, I'll now be up at the point 0, 2, but it is shifting upwards from the blue function. So if I take my blue function and shift it up, I'll get y equals negative x cubed plus 2. And so there, that green function would be my answer. That is, in fact, the graph of y equals negative x cubed plus 2, or at least the shift of it. Now, when you have multiple transformations happening inside, when you're dealing with x's, again, things basically go backwards. So let's look at the example. Let's graph y equals the absolute value of negative x plus 1. As before, we want to recognize this as a transformation of a basic function we're familiar with. Now, in this case, the basic function we're familiar with is going to be the absolute value function. And then there's going to be some changes happening inside. We have a negative 1 multiplying. That's going to create a reflection. And we have a plus 1. That's going to create a shift. So the negative 1 multiplying by the x is going to cause a horizontal reflection around the y-axis. That's what multiplying a negative 1 by the x in a function does. Then the plus 1 here gives us a not vertical, still horizontal. It's going to give us a horizontal shift, and it's going to be to the left by 1. Again, left because the stuff inside, the horizontal stuff, behaves sort of backwards. And as I mentioned before, we are also going to apply these transformations in backwards order of operations. So we're going to apply horizontal transformations in backwards order of operations. So, normal order of operations says that multiplication comes before addition. So we are going to apply these two in the opposite order. That is, we're going to shift first, then reflect. So let's go ahead and do that. Now the graph of just the absolute value of x is one that we are familiar with. It looks like it has a V shape like this. And I'll go ahead and plot a couple of points because we're going to use that in a moment to check our work. So let's plot the points, 3 points that we know are on the graph, 0, 0, 2, 2, and negative 2, 2. And this is the graph y equals the absolute value of x. So the first thing that we're going to do, applying our transformations in reverse order of operations, is we're going to shift everything left by 1. So the point 0, 0 goes to the point negative 1, 0. The point negative 2, 2 goes to the point negative 3, 2. and the point 2, comma 2 goes to the point 1, comma 2. And this is the graph of y equals the absolute value of x plus 1. Because all we've done is we've shifted to the left by 1. And now we're told that we have to reflect around the y-axis. So now each one of these points that we have graphed is going to go to its opposite point on the other side of the y-axis. And again, we can accomplish this numerically by simply multiplying the x-coordinates by -1. So the point -1, 0 will go to the point 1, comma 0. The point 1, comma 2 will go to the point -1, comma 2. And the point -3, comma 2 will go to the point 3, comma 2. And so we get this set up here. So now the blue line is the graph of y equals the absolute value of -x plus 1. So we did this in 2 steps. First, we shifted the graph horizontally by 1, and then we reflected it around the y-axis. And by making sure to do them in the correct order, we were able to make sure that we got things right. Now, the other way that we have of making sure that we've got things right is just to check our work. To check the work, we want to make sure that the points on our graph are solutions to the equation, or input-output pairs for a function. Same thing. So let's check the point 1, comma 0. We want to say, is y equal to the absolute value of negative 1 plus 1? What we're doing is we're taking the original function, the original equation that we were trying to graph, and seeing does it give us true statements when we plug the points in the graph into them. And in this case, we can see the answer is yes, because 0 is in fact equal to the absolute value of -1 plus 1, because the absolute value of -1 plus 1 is 0. Let's take the point 3, comma 2. We could check this and say, does 3 equal the absolute value? I'm sorry, I have that backwards. I've got 2. That needs to equal the absolute value of -3 plus 1. And we see again that this is true, because this tells us that 2 is equal to the absolute value of -2, which is completely correct. And we can check the other points on the blue graph and see that they are all correct also. So this is how we handle things when we have multiple transformations happening inside the basic function. We apply them in reverse order of operations. Now, there is one more transformation that we have to work with, but we've actually already covered basically all of the difficult things that can come up, all the complexities that can come up in applying these. So scaling will be a fairly straightforward process to apply here. So let's talk about scaling. And we'll just do a couple of examples, and we'll see what happens here. Let's look at the graph of y equals 2x squared. And we're going to look at the graph of y equals 1/2 x squared. Now, rather than going through the plotting a whole bunch of points, I want us to think a little bit more um, analytically and say that if we compare each of these to the equation y equals x squared, let's see what happens. And let me go ahead and give us a graph for this. 1, 2, 3, -1, -2, -3, 1, 2, 3. Oh, oops. 4, 5, 6, 7, 8. Let me go ahead and graph out y equals x squared. Again, we've done this a few times now, but working with familiar functions is often a good way of understanding new concepts. So it's got the point 0, 0, 1, 1, 2, 4, -1, 1, and -2, 4. So there's the graph of y equals x squared. So now let's think about y equals 2x squared. Now, for a point to be a solution to this equation, the y values here are going to have to be twice as big as the y values would have to be in the red equation, y equals x squared. And so in particular, notice that some solutions to this equation can be gotten by just taking equations to y equals x squared and doubling the y value. So some solutions here are 1, 2, 2, 8, -1, 2, -2, 8, and again 0, 0. If you plug these xy pairs into this equation, you will get a bunch of solutions to the equation. Now, if we plot those out, we get the following. We get the point 0, 0. We'll get the point 1, 2. We'll get the point 2, 4. -1, 2, and I'm sorry, 2, 8. Sorry, -2, 8. And we'll get a graph that looks like this. And so, what's happening here? Well, each of the y values of the points on the graph are being multiplied by 2. Another way of thinking about this is that we're taking the graph and we're stretching it, we're elongating it. Every point is getting twice as far away from the x-axis as it was before, because the y value measures how far away a point is from the x-axis. So the point 1, 1 shifted up to the point 1, 2, the point 2, 4 up to 2, 8, and similarly over here. So we've stretched the graph out vertically. So let's see what happens with y equals 1/2 x squared. Well, we can do the same sort of thing. For any point that is a solution to the graph of y equals x squared, if we just change the y value to half of what it was before, we will get a solution to the equation y equals 1/2 x squared. So all of these green points, 1, 1/2, 2, 2, -1, 1/2, and -2, 2 are all solutions to the equation y equals 1/2 x squared. And the way that I'm getting these numbers, is that I'm simply taking solutions to the original equation, y equals x squared, and I'm cutting their y values in half. I'm multiplying their y values by a half. And so this is what happens when you multiply a number on the outside of a function. 2 times x squared stretches the graph of the function out by a factor of 2. 1/2 times x squared compresses the function down by a factor of 1/2. And this sort of process is called scaling. And vertical scaling works exactly this way. You simply multiply the y values of the points on your graph by whatever number shows up in front, 2 or 1/2 or whatever it is. So let's look at what happens with horizontal scaling. This was vertical scaling. We're stretching and squashing everything vertically. Let's look at horizontal scaling. Let's compare y equals the square root of x and y equals the square root of 2x. So just as before, I can choose some particularly helpful values of x to make this problem easier. So 1, 2, 3, 4. So here the change that I've made is I've multiplied 2 on the inside of this function. Instead of the square root of x, I now have the square root of 2x. I've applied the square root before the, I've applied the multiplication by 2 before the square root. Now, again, I'll use red for the basic y equals square root of x function, which we know contains the points 0, 0, 1, 1, 4, 2, and 9, 3. So now let's find some points that are on the graph of y equals the square root of 2x. So if x is 0, the square root of 2x is 0. Now we can try and be clever about this. If x is 2, then the square root of 2x becomes the square root of 2 times 2, which is the square root of 4, which is 2. So that gives us another point on the graph. Let's see, if x is 1, then we get the square root of 2. That's not real nice to work with, so we'll leave that. We'll leave that for now. But maybe we can be even more clever about this. What if we took an x value of 1/2? If x was 1/2, then the square root of 2x would be the square root of 1/2 times 2. 1/2 of 2 is just 1. So this is just the square root of 1, which is 1. So this gives us a clue as to how we might do things. So what if we chose 9/2 here? If we let x be 9/2, then the square root of 2x would be the square root of 2 times 9/2, which would be the square root of 9, which is 3. So this gives us something we can work with. We have the point 0, 0 on the graph of y equals square root of 2x. We have the point 2, 2. And we have the point 1, square root of 2, but I can't graph the square root of 2 super easily, so I'm going to skip that one. I'm going to go to the point 1/2, 1. There's the point. Let me try to keep things relatively clean. There's the point 1/2, 1. And then the point 9/2, 3. Now 9/2 is 4.5. So we have this point 9/2, 3. And in fact, we can do more. It turns out that if that we can get the point 8, 4 here also. Now, the red graph and the blue graph compare in a couple of different ways, but we know that when we are affecting the inside of the function, when we're affecting the x before the function like square root of x happens, we want to consider what's happening horizontally. And what we can see here is that what's happened is we've compressed things horizontally. If we take the red graph and we squeeze it together, then we'll get the blue graph. In fact, notice that every one of the points on the blue graph comes from a point on the red graph that we get by dividing the x coordinate by 2. Now that's where this 2 is showing itself here. Now once again we see that we have things working a little bit backwards when we're dealing with x's. When we're dealing with x's, before inside the function, multiplying by 2 means that we're going to divide each of the x coordinates in our function by 2. Similarly, if we had a function of 1/2 out in front here, then that means that we'd be dividing everything by 1/2, or in other words, multiplying by 2. So when you have a number bigger than 1 being multiplied by the x inside a function, that's going to compress the function down. And when you have a number smaller than 1, that's going to stretch the function out. So let's combine together, let's summarize these two rules for scaling. So the graph of a f of x, y equals a f of x, I should say, is the graph of f scaled by, vertically by a. So in other words, we are going to multiply each y value by a. The graph of y equals f of bx is the graph of f scaled horizontally by 1 over b. That is, we multiply each x value by 1 over b. Or in other words, we divide each x value by b, which is the same thing. All right, let's combine all of these together and look at the function that we were dealing with as our example at the beginning. Let's graph the function f of x, which is -3 times 1/2 x plus 1 squared plus 4. So there are a lot of things happening here, and we want to identify each one. So let's break it up carefully. So first of all, we want to identify what the base function is that we are transforming. And in this case, it's the function x squared. That's the basic function that we're working with, and all of the other changes to the function can be described in terms of the transformations we've looked at here. So you've got an x inside, and then we've got a 1/2 being multiplied by the x, and a plus 1. So let's see what each of these are going to do. The plus 1 is going to shift us left by 1. That's what adding the 1 inside does. That's a translation. This 1/2 here, this is a scaling that we just looked at because we've got a number being multiplied by the x. And so this is going to give us a horizontal scaling by 1 over 1/2, or in other words, 2. We could think of the horizontal scaling as always as scaling by the reciprocal of x, reciprocal of the not the reciprocal of x, the reciprocal of the coefficient of x, the number being multiplied by x. So this is going to be multiplying each of our x values by 2, or in other words, stretching the function out horizontally. All right, now we've got a couple more. We've got a negative 3 and a plus 4 over here. Now, this plus 4 on the outside is going to be a vertical change because it's happening outside the base function of x squared. So this is going to say we shift up by 4. Now, the negative 3 here, we could think of in 2 separate ways, but we'll see that we can actually sort of combine the two. So the negative here is going to say reflect across the x-axis because it's on the outside, which means it's a vertical reflection, and a vertical reflection is across the x-axis. And the 3 here is going to give us a vertical scaling by 3. Now, the trick here is that when we have both a reflection and a scaling, we can actually combine those together. And combined together, these two things just say to multiply each y value by negative 3. So we have four separate transformations that we need to do because 5 if we consider the reflection and the vertical scaling separately. So let's go ahead and do this. And what we're going to do is we're going to focus on the points again. We're going to start with the points on the original function 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. Here's our original function, y equals x squared. So now let's go ahead and do some of these transformations. And of course, we don't want to do all of these transformations at once. We want to do them in steps. In fact, we're going to do a few of these. And when we have so many of these transformations we're going to do, what I'll usually do is do 1 or 2 translations on a single set of axes and then move over to a new one. Otherwise, things just get really messy. So here's our original. When we apply our transformations, I like to work from the inside out. I do all my horizontal transformations first, then I'll do all my vertical ones. Now remember, when we do these transformations, we have to do them in the correct order. Inside the function, the horizontal transformations go in opposite of order of operations order, which means that we're going to do our shift with the plus 1 before our scaling involving a multiplication by 1/2. So our first transformation is going to be shifting left by 1. Then our next transformation is going to be a horizontal scaling by 2. Then we're going to take the move to the vertical transformations, and the vertical transformations happen in the order of operations order, which means that we're going to multiply each y value by negative 3 next, and then finally we're going to shift up by 4. So we're going to do these 4 transformations in this order. So let's go ahead and do that. First, we shift left by 1. So each of these points are going to shift to the left by 1. We'll get negative 1, comma 0, negative 2, 1, 0, 1, 1, 4, and negative 3, 4. Now here's a little trick. I'm not going to sketch in the green graph, the green parabola here. It's only going to make the problem more, or the graph here more confusing. I'm going to just leave it here for a second and translate my points over when I'm closer to to getting to my answer. So the green points are the points after the first shift. So green points are points in the graph after applying the first transformation. Next, we're going to apply the second transformation. We're going to do a horizontal scaling by 2. And what that means is we're going to take each one of our green points now, and we're going to multiply their x-coordinate by 2. We're going to stretch everything out by 2, by a factor of 2. So this point 1, 4, for instance, goes back to the point 2, 4. The point 0, 1 stays at the point 0, 1. The point negative 1, 0 goes to the point negative 2, 0. The point negative 2, 1 goes to the point negative 4, 1. And the point negative 3, 4 goes to the point negative 6, 4. Now, as you can see, this is a bit of a mess. So at this point, we're going to switch over to a new set of axes. However, notice that I'm just doing this by applying my transformations to the individual points. So we shifted left by 1 and then multiplied all of our x values by 2, and that gives us our setup. All right, so now we're going to need our next graph, and because I know sort of what's coming, I'm going to give myself plenty of room here. And we'll go like this. All right, so let's see, where are our points? We've got the point 1, 2, 3, 4, 5, 6, 4. All right, so we've got the point negative 6, 4. We have the point negative 4, 1. We have the point negative 2, 0. The point 0, 1. And the point 2, 4. So these are the points that we get after we do the second translation. So next we need to do the third translation, which involves multiplying each of the y values by negative 3. So let's do that. Let me go back to red for this. So the third transformation we've got is a reflection across the x-axis, so it's going to turn down like that, and it's going to stretch out. And we're going to do that by multiplying each of the y values by negative 3. Now the point negative 2, 0, if you multiply that y value by 3, you get back to negative 2, 0. The point 0, 1, you multiply that y value by negative 3, and you get to the point 0, negative 3. Negative 4, 1 gets translated to negative 4, 3, or reflected and stretched to negative 4, 3. And then the point 2, 4 gets translated to 2, negative 12. So that's going to be down here, 2, negative 12, and then 6, negative 12. So that gives us the graph after 3. So we've done three of our transformations. We shifted to the left by 1. We scaled horizontally by 2. We multiplied each y value by negative 3, which encompassed a reflection and a scaling. And finally, we're going to shift up by 4 in order to get our final result. All right, so let's see what this is going to look like. I'll go ahead and do it in green for the final one. So shifting up by 4, of course, just means that we're going to take each one of our points and move it up by 4, add 4 to the y coordinates. So we get negative 2 comma 4, 0 comma 1, and negative 4 comma 1. And then we'll have 2 comma negative 8. And then negative 6 comma negative 8. And there is our graph of y equals negative 3 times 1 half x plus 1 squared plus 4. This process is, of course, time consuming when you have so many transformations. The good news is that most of the time, the functions that we deal with involve only one or two of these transformations at a time, and often only one horizontal transformation and one vertical one. However, by carefully applying the transformations step by step by step, you can graph many functions that are built up out of the basic ones that you already know.